So for us to be able to calculate and simulate a UV vis spectrum, what we first have to do, right, is go through, do a geometry optimization, frequency vibration calculation, make sure that the frequency vibration calculation, right, that worked successfully. So I'm just checking right here the one that I did. So I can see here, there are no negative modes, so we're all good. So what we do now is we'll just go click left, or not left, sorry, the next arrow. And so we'll go here. So now we just choose the UV vis calculation corrected. So the one that we're using is B3 lip. And so here, let me give the label UV vis. Right, so we have then, the method, the basis set, the auxiliary basis set, and then here under advanced, the things that we can do, right? One thing I would recommend is for these calculations, once they start getting bigger, to use Rij cos for, the geometry optimization, the frequency vibrational calculation, right, for the UV vis, just because it'll speed it up. And I'm showing that in a different video, kind of the difference and the benefit of doing that with just a minimal amount of error that gets introduced in those cases. So we have Rij cos x selected. The next thing that we want to make sure that we pay attention to is the number of roots. So this actually calculates how many, electronic transitions we want the calculation to do. 50 is a pretty good number, right? You can have it be lower if you're only really looking at a few of the earlier ones. You can go up to 100, and higher and stuff. But the more roots you have, the longer the calculation takes because it has to calculate more of them. So now we can just go ahead and submit this. Now that the calculation's finished, we can look at it. And so if we scroll down, right, what we'll have here is the excited state section. So this is where essentially, all the data on your UV vis is going to be shown. So we can see right here, the energy in nanometers, right? So this is where the peaks are going to be located. So we can see that the lowest energy is actually pretty low in intensity, but that doesn't necessarily mean that isn't important, right? So, the formethoxyazobenzene actually is a colored dye. And so most dyes and most pigments actually have within the visible region really low intensities, but just because they're the only thing there, right? You don't really need that high of an intensity, especially compared to all of these other transitions right here. So we have, all of these that we can look at. And so you can, change the units from nanometers into electron volts if you wanted to, right? So it can give it to you in those values if you're more comfortable with that, but nanometers is probably the best thing that you would want to plot your spectrum with. And so then here, right, we can plot our UV vis spectrum. And so we get our spectrum right here. And so one important thing to, pay attention to again is that you can change what the line width is. So currently it's set to 50 nanometers, but if you're like, oh, well, I have a really sharp spectrum, let's see what that looks like. You can change that here. So now a lot of those peaks that were previously kind of, being parsed out into different overlying peaks in the previous 50 nanometer one, now with 10 nanometers, right? Everything kind of gets more visible. And so again, if you have experimental data that you're comparing this to, you kind of want to play around with that width to get an idea of, what actually matches the width that we're seeing in the experimental data. Now, another important thing to look at is that you probably want to know, well, what transitions are actually happening, right? What orbital is an electron starting from, and where is it going to for each one of these transitions? So to do that, you have to go into the raw output. And so then if we scroll down to the TD-DFT excited states portion right here, what we can see is all the different states. So the first thing that we can notice is that, the first state, that lowest energy one, the one that comes in at, 2.629 electron volts, which is, this in wave numbers. And if you were to convert it into nanometers, right, that's the one that's at like 470. We can see that this is a transition from, the 54A, orbital to the 56A orbital, right? And so the A is just simply the spin. And so in a case where all the spins are lined up, it doesn't matter which one it is. It's going to be exactly the same. So we can see that that's what this peak right here is. So 54 to 56. So if we look at this, what we can see, and we scroll down, right, we have the molecular orbitals right here. And so we can see here. And so one thing to point out is that Orca actually within its file, it starts everything at 0. So what we would typically consider like the first orbital would actually be considered orbital 0 within the list. And so we can't directly use 54 and 56 in this case because that wouldn't make any sense, right? 54 is a filled orbital, right? 56 is a filled orbital in this case. And so you can't fill, have an electron go into one that already has 2 in there. And so in reality, what we're really looking at is the 55 to 57 transition, right? Because what we have to do is subtract 1 from these numbers, right? And then we get what the actual ones are from the output. So we're going from 55 to 57. And so a nice thing to do is kind of think about like, okay, well, what do these orbitals look like? And what is that transition, in reality? And so if we, look at 55, so that's the one below the HOMO orbital in this case. So we can just go here and we can work our way through, right? So we have 55. And so we can see that this is, primarily a sigma bonding orbital between the that bridging nitrogen species right there. And then we're going to 57 in this case, right? Because that's, one higher than the 56 that we saw in the thing. So if we're looking at this, and so now we can see right here, right, we're going into essentially the next orbital within that, series, but where we have one node in between those nitrogens, right? And so that's what we're being excited into. Is essentially, primarily, this exists within that, dinitrogen bridge that we have in these cases. And so, those are important things to think about when you're thinking about UV-Vis spectra is, what are the starting orbitals? Where are they going into? And then thinking about like, how does that affect our, the physical properties and like, what can you do with that, right? When we think about reactivity, especially any reactivity that involves light, you want to, either promote electrons into an orbital so that way you can, destabilize something and have a reaction happen, or you want to, remove an electron out of an orbital and then again have an electron happen, a reaction happen with those orbitals. And so, those are the things to look for and pay attention to in these cases.